We discussed Leibniz rule today. Okay. We'll discuss the general Leibniz rule as well as the simplified Leibniz rule. Normally questions are asked on the simplified one. We start with the simplified one and then we move on to the generalized Leibniz rule. And where to use the simple Leibniz rule and where to use the generalized Leibniz rule. This is what we have to understand. Okay. Overall, the topic is very simple. Very small topic, so we finish off with this class itself. Let us see the formal statement for Leibniz rule. So if the function fx and gx are defined on AB and differentiable at a point, let's say for instance it is differentiable at x, which belongs to the open interval AB, then the Leibniz rule, this is the simplified version. This is the simplified version of your Leibniz rule. The differentiation of integration fx to gx, phi of t dt, is given by phi of gx into d by dx of gx. Okay, phi of gx, whatever is this function, phi of gx. Phi of gx means this one, phi of gx into differentiation of gx minus phi of fx into differentiation of fx. Okay. Normally, remembering, you don't need to remember this, you just need to understand the structure and apply this in the question. Okay, phi of gx and everything, just understand the structure. We see the examples and then this will be clear to you. Okay, once you see the examples, this will be very well clear to you. For example, let's take this one only. Let me show you one example here itself. Let us take one example of let's say you want to differentiate integration x squared to x cube 1 by log of t dt. Here one observation is this function is only a function of t actually. Okay, function of t, and the limits are variables in this case in terms of x. Okay, so overall when you integrate this actually turns out to be the function of x itself, isn't it? When you integrate these are all what? These are basically the limits of t. T is equals to x squared to x cube. When you integrate this part, you will get something, function of x. When you put the limits, you will get function of x. Then you will differentiate. That will turn out to be a function of x, which means you have to differentiate with respect to x. Okay. So this overall function in integration, everything, integration of 1 by log t, whatever it is, phi of t dt, this entire function is actually a function of x. Okay. Integrand is a function of t. Entire function after integration is a function of x. Now what I do, we want to differentiate this, but the limits are going from x squared to x cube. We want to differentiate this integration actually. Okay. So we apply the Leibniz rule in this case, simple Leibniz rule. What we have first, phi of gx into d by dx of gx. So phi of gx means here gx is x cube. So phi of x cube, which means 1 by log x cube in this case, isn't it? 1 by log x cube. Okay, this is phi of gx actually. Phi of gx in this case, what is phi of t? Phi of t is, this is phi of t. This is phi of t. Okay, this is gx. And this is your fx. Clear? This is gx and this is fx. So phi of t, fx, gx. So first what we have, phi of gx. Phi of gx means phi of x cube, and phi of x cube means this is phi of t. So phi of x cube will be 1 by log of x cube. Then we have differentiation of gx, differentiation of x cube, differentiation of x cube minus phi of fx. Now similarly we have phi of fx, this is phi of t, so phi of fx will be phi of x square. So in this case this will be 1 by log x square, okay, into differentiation of fx, that is basically x square. Now you simplify this thing, so 1 by log x cube, you can write this as 3 times log x if you want to simplify this a bit, into differentiation of x cube, that is basically 3x square, minus this is 2 times log x Differentiation of x square, this is 2x. So here we can see 3 and 3 cancels out, 2 and 2 cancels out. Here we are left with x square by log x and x by log x basically. So what we have, if you simplify, this is x square minus x by log x. If we take the LCM as log x, so that's basically x square minus x by log x. So this is the overall concepts of Leibniz rule. Okay. Integration will be there. Differentiation of this integration, definite integral, which is over some variable x, function of x, function of, you want to integrate some function, the integrand is a function of t, and the variables are from fx to gx, the function of x are there. Okay, it can be anything. I'm just saying, this is just for example, like this can be function of t, this can be function of x also, whatever it is. They are asking for d by dt of this thing. Okay, overall the concept should be clear to you, like what is the function, overall function. If suppose this like this Leibniz rule can be stated of in this manner also, d by dt, if we change the variables over here, isn't it? If we make this a function of x, suppose phi of x dx, okay, overall this will be x is equals to t square to t cube, like this, t square to t cube. Then this would have been a function of t in that case. Okay, this would have been a function of t. After integration, this would have been a function of t. Then we would have differentiated with respect to t in that case, d by dt of this thing. So whatever are the limits actually, after putting those limits, whatever is the result, that is your function, function of t, function of x, whatever it is. Clear? Let's do some questions first and then we'll come to the generalized Leibniz rule. Chalo, first question. Easy one, JEE problem. You have to evaluate this limit. So this is given in terms of limits. Okay, it is a limit question actually. Limit x tends to infinity. Numerator we have integration 0 to 2x t times e to the power t square divided by e to the power 4x square. Now what we can observe from here actually. First of all, one thing we can see, this is of the form infinity by infinity, isn't it? This is actually of the form infinity by infinity. You put x tends to infinity, this everything tends to infinity over here, this also tends to infinity, isn't it? If you use the if you just put x tends to infinity over here, this 0 to infinity, this will turn out to be, and this is actually after you integrate this thing, this is simple to integrate actually, you will find out this is actually, the result will be in infinity and this will be also infinity. So this is actually of the form infinity by infinity. Yes, correct. So definitely we'll use the L'Hopital's rule in this case. If we use the L'Hopital's rule, which means you have to differentiate numerator and the denominator. Now to differentiate the numerator, we will use the Leibniz rule in this case. Simple. Okay. So we differentiate the numerator. So we have limit x tends to infinity. If we differentiate the numerator with the help of Leibniz rule, this is simple. We have phi of gx in this case, fx is 0, gx is 2x, simple. Okay, so this will be what? This will be 2x times e to the power 2x square, okay, into differentiation of 2x, that is 2. Okay, divided by differentiation of e to the power 4x square, that is basically e to the power 4x square, into differentiation of 4x square, that is basically 8x. Okay, clear? So now we simplify this now. So this is actually limit x tends to infinity. Here we have 4 and this is 2. So you can take out half outside. So this is limit x tends to infinity. Here we have e to the power 4x square. Okay. And denominator what we have? Denominator we have x also gets cancelled out. Here we have x cancelled out and here we are left with e to the power 4x square. Okay. So what is this? This is actually 1. So we have half. So half is the answer. Okay. This also gets cancelled out. So we are left with half. You can directly cancel out from here itself, which is simplified version I have shown to you. Okay. Answer is half actually. So this is the previous year JEE problem, quite easy. Okay, next we have this problem. This is also a JEE problem. F such that R to R be a differentiable function having f of 2 is equals to 6, f dash of 2 is equals to 1 by 48. Evaluate this limit. F of 2 is given, f dash of 2 is given. You have to evaluate this particular limit. One thing we can observe, we have limit extends to 2 actually. Okay. So first of all, one thing you can observe, as limit extends to 2, this will tend to be f of 2 and f of 2 is 6. Integration 6 to 6, this will automatically turn out to be 0. You can simplify this and write it in this manner. What I'm trying to say, this is limit extends to 2. Actually, this integration involves the function of x. Okay, and this is dt. So with respect to t, actually the function integrand is in terms of t. So x minus 2 is a constant with respect to t. Actually, we are doing the integration with respect to t. So x minus 2 is a constant. So we can take out this thing. Basically, we can take this integral in the numerator part. Actually, we can simplify this and write it as integration 6 to fx 4t cube divided by x minus 2. This way we can write it. As limit extends to 2, why we are doing this thing? Don't take this outside the limit because we have this limit involved in this case. Limit extends to 2 over here. We are writing in this manner because this integration, this integrand actually depends on t. Integration depends on t. We are integrating with respect to t. Okay, t is equals to 6 to fx. So with respect to t, x minus 2 is a constant in this case. So we can take out this outside the integration, or rather we can take this integration in the numerator. We can write it in this manner. Now if you figure out from here, limit x tends to 2, you put x tends to 2, this will tend to f of 2. F of 2 is 6 in this case, integration 6 to 6, this means this will automatically turn out to be 0. And divided by x minus 2, over here you put x tends to 2, this 2 minus 2, this will be 0, so this is 0 by 0 form. So again we apply the L'Hopital's rule. Now we apply the L'Hopital's rule means we differentiate the numerator and denominator individually. If we differentiate the numerator, once again we have to use the Leibniz rule in this case. So we have limit x tends to 2, integration 6 to fx 4t cube. How do we differentiate this? Simple, Leibniz rule. So we have this will be 4, you can take outside, this is basically constant, so you can take outside this integral part. So this is how much? So this is 4 times fx whole cube into differentiation of fx, that is basically f dash of x, isn't it? Clear? Into f dash of x divided by differentiation of x minus 2 with respect to x, that is 1 basically. So now the 0 by 0 form is gone. If you put the limit over here, so this turns out to be 4 times fx whole cube, f of 2 whole cube multiplied by f dash of 2, right? And we all know these values, it's given in the question. F of 2 is given 6, f dash of 2 is also given 1 by 48. So this is basically 6 cube into 1 by 48. Okay, so now just simplify this, you'll get the answer. Okay, so 6 into 3, that is basically 18. 18 is the answer. Sure, next one. Okay, let's do this problem. We have a function defined from 0 to infinity to r. And we have one more function fx, capital Fx is integration 0 to x f of t dt. Fx square is equals to x square into 1 plus x. We have to find the value of small f of 4 actually. How do we do this? First of all, we have this function fx, capital Fx is given. Okay, integration 0 to x f of t dt. So we need f of 4. So this small f of t is actually there inside some integrand. So we have to remove this, isn't it? We have to remove this part actually. Also we have f of x square. F of x square is this thing is given. So what is f of x square actually? From here we can find out f of x square. What is f of x square? Simply replace x by x square. F of t dt. Okay. And f of x square is given, so we can replace this. We can write this as x square times 1 plus x, which is equals to integration 0 to x f of t dt, 0 to x square f of t dt. Okay, because f of x square is known to us from here. What we need? We need f of 4. So we need to find first f of x, then we find f of 4, isn't it? Or some relations. Basically, we need to find some relations of f, small f. In order to find this thing, we need to remove this integral, so which we can remove by Leibniz rule. One of the very fundamental application of the Leibniz rule is to find out the function actually. The function is stuck inside some integration. To remove that integral, we can differentiate with the help of Leibniz rule to get the function. So this is one of the foremost and the fundamental application of Leibniz rule, where we find out the function by using the Leibniz rule. So what I do, I differentiate this, simple differentiation. Okay, that's basically x square plus x cube. If you differentiate this, so what I get, I have 3x square plus 2x. If you multiply this, you will have x square plus x cube. So we have 3x square plus 2x. And we differentiate this right hand side with the help of Leibniz rule. So we have f of x square into differentiation of x square, that is 2x. Clear? Fine. So we need f of 4 in this case. So we can solve for f of x square. Okay. If we solve for f of x square from here, f of x square will be 2x plus 3x square divided by 2x. This is f of x square. We can take one x common and then we can simplify. So we have 2 plus 3x divided by 2. X cancels out from here if you take one x common. So this is your f of x square. So f of x square is 2 plus 3x divided by 2. Now to get f of 4, we can replace x by 2. Okay. If we replace x by 2, so we have f of 4 from here. Okay. 2 plus 3 times 2 divided by 2. So we have 2 plus 6 divided by 2. 8 by 2, that is 4. Okay, fine. Sure, next. All of you try out this question. Find the least value of the function phi of x. Phi of x is the function. Integration going from 5 pi by 4 to x 3 sin t plus 4 cos t dt on this interval. You have to find the least value of this function in this particular interval, 5 pi by 4 to 4 pi by 3. Try to solve this question. Find the least value. This is overall a function. Function fx, phi of x is given, and this is a function of x. Limits are involved in terms of x. So after you integrate this thing, you will get some function of x, isn't it? You put the limits, integrate this thing, integrate it in terms of t. After you integrate, put the limits, you will get some function of x. Phi of x will be some x function, and then you will differentiate with respect to x. So try out this question. You have to find the least value of this function. Okay, so they are asking for the minimum value of this function, phi minimum of this thing. So we need to differentiate this and see the resultant, that whether this is decreasing, increasing function first, whether in this interval. So one thing clearly we can see, you find out phi dash of x. What is phi dash of x? 3 sin x plus 4 cos x. Okay. Remaining part is 0 because we have 5 pi by 4 in this case, isn't it? 3 sin x plus 4 cos x. Now in this case, this is phi dash of x, this part, interval is given 5 pi by 4 to 4 pi by 3. This interval is given. So in this interval, you will check at the extreme points, see the function is decreasing function. See at the extreme points, the function is decreasing function. Okay. The decreasing function means the graph will be somewhat like this. Isn't it? This is a decreasing function. One of the least value of the function, the least value of phi x can be obtained at x is equals to 4 pi by 3. Isn't it? The least value like this. Least value of the function can be obtained at 4 pi by 3. Okay. And the maximum value of the function can be obtained at 5 pi by 4. One of the least value of this phi of x can be obtained at x is equals to 4 pi by 3 and the maximum value will be obtained at x is equals to 5 pi by 4 since the graph is decreasing. So find out what is f of phi of pi 4 pi by 4. Okay. Find out what is phi of 4 pi by 3. What is phi of 4 pi by 3? That is basically integration 5 pi by 4 to 4 pi by 3, 3 sin t plus 4 cos t dt. Integrate this. Tell me what is the answer. Integrate this, you will get the least value from here, because at 4 pi by 3 we will have the least value. Graph is decreasing. 4 pi by 3 we will have the least value. So at this particular value 4 pi by 3, we have phi of 4 pi by 3 will be integration 5 pi by 4 to 4 pi by 3. When you integrate this thing, whatever is the result, that is your least value of this particular function. Find out this. What is the least value of this? Simple question. Okay, so I hope this is simple integration. You all can try out this. Try out. Leaving this simple integration for you. You all can try out this. Those who have done, it's fine. Those who haven't done, you will try out this as your homework. So let's move to the next one. Okay, before doing this question, let us do the generalized version of your Leibniz rule. Then we can come back to this question. So what is the generalized Leibniz rule? So suppose you have function phi x and psi of x which are defined on AB and differentiable at some point. Let's say x belongs to open interval AB, and f of xt is a continuous function. So this is what we have, the differentiation of, once again, this is overall a function of x because limits are from phi of x to psi of x. After integration, you will have some psi of x. But in this case, the function involved, integrand, is function of both x and t. Function is not only involving t, it is also involving x also, x and t. But we are integrating with respect to t. So we have the function integrand is a function of x and t, and also we are integrating with respect to t in this case. But overall, whatever is the result, this will be overall the limits are from phi of x to psi of x. So basically the limits will be in terms of, after integration, this will be in terms of x only. So to differentiate this, we have the generalized Leibniz rule, which is integration phi of x to psi of x, del m by del x phi f of xt dt. Now del by del x means partial derivative with respect to x. So whenever you are differentiating partially with respect to x, which means t is to be kept constant. This is basically partial derivative. Any other variable except whatever you are differentiating with respect to, except that variable, every other variable is kept to be constant. T, z, whatever it is. We are differentiating with respect to x partially, which means Other variables like t and all will be kept as constant. Okay, and the remaining f of x comma phi psi of x d by dx of phi of x minus f of x comma phi of x into d by dx of phi of x. You can relate this much part actually from the previous Leibniz rule itself. Okay, there's a similar part from the previous Leibniz rule itself. You're simply replacing the t part by psi of x and phi of x minus of this thing, and then simply differentiating whatever is in the limits actually. Okay. Now, when to apply the simplified Leibniz rule and when to apply the generalized Leibniz rule? This you have to understand. Okay. Whenever the function involved, this integrand actually, if the integrand is independent of those variable which is involved in the limits, okay, then we apply the Leibniz rule, simplified Leibniz rule. If the integrand is independent of those variables, only function of t is there, this is function of x, then you can apply the simplified Leibniz rule. Otherwise, if this integrand is not independent, it is dependent on the variables which is involved in the limits. This is also a function of x, this is also a function of x, here also we have x. So in this case, we will apply generalized Leibniz rule. Okay. This situation you can understand from the both of these rules actually. So whenever we have this integrand is involving some function, both the functions are involved, simply apply generalized Leibniz rule. Otherwise, apply the simplified Leibniz rule if only function of t is there. Now let's do that question. Now we can do this question. F of x is integration 0 to x square minus t square g of t dt. G is a real valued continuous function. We have to find f dash of x. Simple problem, simple application of the generalized Leibniz rule. So we have to find out f dash of x. Let's find out what is f dash of x. F dash of x will be what? So first what we have? First we have integration 0 to x del m by del x. Del by del x of f of x t dt, isn't it? Integration, first I'll just simply write down this for you not to get confused. So recall d by dx of integration phi of x to psi of x dx, f of x t dt. Okay. This is given by what? This is given by the generalized Leibniz rule. We have integration. First we have phi of x to psi of x. Okay. Del by del x f of x t dt plus f of x comma psi of x first into differentiation of psi of x, isn't it? Normal differentiation. And then minus f of x comma, replace t by phi of x now, into differentiation of phi of x. Now use the same thing over here. We have, this is the generalized Leibniz rule. So find out what is f dash of x. F dash of x will be, first what we have, integration phi of x to psi of x. Now phi of x is 0, psi of x is x. So simply integration 0 to x. Now del m by del x of f of x t dt. So del m by del x of f of x t, integrand, that is basically x square minus t square. Okay. G of t dt. G of t was also there. G of t dt. This is the entire integrand actually, including this g of t dt. Then plus what we have, f of x comma psi of x. So this is f of x t. This is f of x t. Fine. So what we have, f of x comma phi of x, that is basically x comma psi of x, that is basically x only in this case, isn't it? So what we have basically x square minus x square in this part, x square minus x square was also there, and in the place of t square we have x square because we are replacing t by x. So x square minus x square into g of x, this will be 0 only, but once you have the practice then you will be able to write down this as fast as possible. D by dx of what, psi of x, that is basically x. Okay, and minus remaining part you don't need to write it because this is the remaining part will be 0 only. This part is 0 only, isn't it? Because this differentiation of here we have 0 itself, isn't it? Phi of x is 0. So anyways this part will be 0 only. Okay, because this differentiation of phi of x, differentiation of 0 will make it 0. So we have integration 0 to x. Let's differentiate this partially. So how will you differentiate partially? Differentiate with respect to x. Remaining variables are constant. Okay. So what we have, differentiation of x square, that is 2x into g of t is a constant. So g of t you can take outside, g of t. Okay. 2x into g of t, and this part will be 0. Minus t square into g of t, this part will be 0 because we are differentiating with respect to x partially. Okay. Clear now? And this part will be also 0, isn't it? This part will be also 0 because x square minus x square is 0. So what I have from here is integration 0 to x, 2 times integration 0 to x, take this 2 outside, x g of t dt. Now x also you can take outside, you don't need to take this x inside because integration is dependent on t variables are there, right? X also you can take outside, so 2x into this thing. Okay, this is your differential result basically, 2x into integration 0 to x g of t dt. This is your f dash of x. Now they might ask for some f, what is f dash of, they'll give you some informations and they'll ask you to find out what is f dash of 4, f dash of 3, like this. This type of questions can be there. Clear? Okay, let's do this problem from ISI 2018. Read this. F is a function from 0 to infinity to r. It is a continuous function such that for all x belongs to 0 to infinity, f of 2x is given to be fx. You have to show that the function g defined by this equation, gx is this function, integration 0 to x to 2x f of t into dt by t, or ft by t dt basically, for x greater than 0. You have to show that this is a constant function. Very simple problem. Okay. To show the constant function, what we can do is we can show that g dash of x is 0. Okay, to show that this is a constant function, show that g dash of x is equals to 0, which will imply that g of x is a constant function. So what I do, I find out g dash of x. What is g dash of x? First of all, gx is this. You can modify gx and write it as gx is basically integration x to 2x. This is basically ft by t dt, where x is greater than 0. So g dash of x will be, simply use the Leibniz rule, simple Leibniz rule, isn't it? F of 2x by x, 2x by 2x into differentiation of 2x, that is 2, minus this will be f of x divided by x into differentiation of x, that is 1. Okay, so here I'm getting some cancellations, 2 and 2 gets cancelled out. So we have f of 2x by f of 2x minus f of x divided by x over here. Now we have got this relation that f of 2x is equals to fx. So generally this is fx, so which means this is 0, isn't it? 0 by x, which is 0. In this case, g dash of x is equals to 0, which means simply g is a constant function. Now in this case, one more thing is, while answering this question, it will be better if you show that when a function's derivative is equals to 0, then the function is a constant function. Show the proof of this part. why we are doing this. Okay, just don't only show this part, just simply show that g dash of x is equals to 0, any function whose differentiation is 0, which implies that function is a constant function. G of x is a constant function. Okay, show this as a theorem or a claim basically. Okay, I have shown the proof in my I think mean value theorem class. I have shown the proof that function's derivative is 0. I have explained there how we can prove that a function's derivative is 0, which implies that the function is a constant function. So next problem. F is one more function defined from 0 to infinity. Domain is 0 to infinity. The range is also 0 to infinity. Okay, codomain is also 0 to infinity. It is a function such that x times integration 0 to x 1 minus t f of t dt is equals to integration 0 to x t times f of t dt. This is given. F of 1 is equals to 1 is also given. You to find out f of x. I told you one of the very fundamental and foremost application of the Leibniz rule is to find out the function itself. Okay, like this is one of the very basic question. What do? You simply differentiate both sides to get the function. That's all. Okay, simply differentiate both sides to get the function. Use these informations, whatever is required. This is a standard problem. Same thing. Function is stuck inside some integral. We have to take out this thing with the help of differentiation. Okay, let's solve this. It is a function such that this is given. So what I am going to do is to take out this function. Obviously, we need to differentiate. So I differentiate both sides with the help of Leibniz rule. Let us see what we can get from here. Okay. So if I differentiate the left hand side is basically x times this thing. So we differentiate with respect to x. No, not 0. I don't know the answer. Maybe it might happen. Let's see. We differentiate the left hand side with the help of product rule. So first we differentiate this x and then this thing times x. Differentiation of this thing times x. So what we have is basically 1 into integration 0 to x. Differentiation of x first, that is 1 times integration 0 to x 1 minus t f of t dt, plus then we have x times differentiation of this thing with the help of Leibniz rule, that is basically x times 1 minus x into f of x, and we are differentiating the Leibniz rule with respect to x. So basically here we have x, right? This is a function of x. So into differentiation of x, that is 1. Okay. And this is 0 only, so minus 0 will be there. So this is equals to integration of 0 to x t times ft dt. You differentiate this, what I get? X times f of x directly. Simple integration. Now we are left with this thing. We can simplify this. What we have left hand side, we have integration 0 to x 1 minus t f of t dt. This function is there, and what I can do is here we have, if you multiply this thing, we have x times fx minus x square fx, isn't it? If you see, if you multiply x times fx, this x times fx and x times fx will cancel down. From the left hand side, the right hand side, this will get cancelled down, and you will have minus x square fx. You can take this on the right hand side. So we have x square fx now. Okay. Once again, the function f of t is still stuck inside some integration. So we once again differentiate this to remove this integral part. If you once again differentiate this, so what I get from here is 1 minus x into f of x, and right hand side we have 2x into f of x plus x square f dash of x. Okay. Clear? Similarly, we can have some sort of simplification from here also. We have 2 times 2x into fx. Here we have minus x into fx, right? If we take this on the left hand side, what I can do is I can make this as 1 minus 3x into f of x, and right hand side we have x square f dash of x. So what I need is actually, I need the function fx actually, right? Till now, you can also observe that we haven't used this information. So we are getting some function, we are getting fx, but also we are getting f dash of x. You will say that if we integrate this thing on the right hand side, if you tell me that I'll integrate by parts, this one, what you will get? You might get certain things, you will get certain cancellations over here, but unfortunately on the left hand side, you cannot integrate. We have fx, you will get stuck over here, right? So we can bring into some standard formats of integration and differential equation, and then we can solve. We can think of this manner. I have f dash of x, one standard form I can clearly see from here. I can bring this as f dash of x upon fx if I bring into this format. F dash of x upon fx, okay. And on the left hand side, this part actually, I can write this as 1 minus 3x upon x square. I can write this entire expression into this manner. Okay. Why we do this? You all know this is a standard form of differential equation actually. If you integrate both sides basically. Okay. This is a standard form of integration. F dash of x upon fx basically. What is this? Log of fx, isn't it? This is log of fx. Okay. Obviously log base c. And this is integration of 1 upon x square, which is basically minus 1 upon x. And this is minus 3 by x. Integration minus 3 by x. That is basically minus 3 log x. Okay. Minus 3 log x is there. Fine. And one constant will be there. So to adjust with the log part, basically take the constant to be log c. Take the constant to be log c. Constant will be adjusted over here, right? Just for the sake of simplification, we take, since c is a constant, log c is also a constant. So this will get simplified now. Okay. Fine. So we can find fx from here. What is fx? We can find fx. Fx will be, this is log c. This is basically minus 3 log x. Okay. What I can do by the properties of log, I can write this as log of fx. So fx will be, now this will be, one thing I can do, take this log c on the left hand side. Okay. If you take this log c on the left hand side, this will be log fx minus log c. Okay. Log fx minus log c, log fx by c. Now if you take the c part on the right hand side, so this fx will be c times e to the power, take the log also, take the log, make this as exponential function. So this is basically e to the power minus 1 by x minus 3 log x. I hope this calculation is clear to all. What I am doing is I am taking this log c on the left hand side. So this is log fx minus log c, that is basically log fx by c. Okay. If you take the log part on the right hand side, this will be e to the power minus 1 by x minus 3 log x, and take this c, cross multiply this c on the right hand side. So this fx will be c times e to the power minus 1 by x minus 3 log x. Clear? Now we need to remove this arbitrary constant from here. Okay. We need to find this exact value of this c. So for which this information is given, f of 1 is equals to 1. Whenever this information is given, we use this to remove this arbitrary constant. Okay. This means x is equals to 1 and y is equals to 1. The value of f of 1 is given. The value of f of x is given to be 1 when x is equals to 1. So you put x is equals to 1 and y is equals to 1, you'll get the result from here. Okay. You put x is equals to 1, so we get f of 1 from here. F of 1 is basically c times e to the power, and this will be log 1 is 0, so this will be e to the power minus 1 from here, right? And f of 1 we know this is given to be 1, so we have c times e to the power minus 1 is equals to 1. So which means c is equals to e in this case. You take this e on the right hand side, so this will be 1 by e, that is basically 1 by e whole to the power minus 1, so that is basically e itself. So c is what? C is e in this case. C is e. So now you can find out the function. So what is the function now? What is the function? Fx is function, you'll get it from here itself. This function, this is your function. Now simply put the value of c. C is what? C is e. So this is basically the function is e times e to the power minus 1 by x minus 3 log x. Okay, and this is basically so just simplify this thing. So we have fx is basically 1 by this thing is there, so plus 1. So just you will get also you just separate this also. We have 3 log x. You can make this as log x cube. So this will turn out to be 1 by x's cube. Okay, just separate the powers. We have 1 by x's cube into e to the power 1 minus 1 by x. This is your function. Okay, so this was comparatively a nice problem. Leibniz rule was also involved. Concepts of differentiation, differential equation, integration, all these things are involved. How to handle those arbitrary constants, all these concepts were involved. Nice question. Clear? Take this problem for your homework. I'll discuss this in my next class.